All right, so we are continuing with chapter 11. We reviewed a little bit graded potentials. They're essential at initiating these action potentials. They are a short distance signal. They sort of decrease in strength with distance, right? Sort of a smaller player. What we really want to focus on here are the action potentials. And these are the primary or principal way that neurons cells send signals. They are a long-distance neural communication. They occur in muscle cells and on the axons of neurons. So that's a lot of places. And so they don't decay over distance. They should, in theory, start at one end and be the same strength or within the same strength at the end as they are at the beginning. The graded potentials start strong and then kind of flatten out over a space. And so this one is you're opening the channels all along the membrane so the strength stays the same all the way down the axon or the dendrite. With the graded potentials, they sort of start in the middle and then that's it. They kind of peter out. So these guys are going to be opening, these action potentials are going to be opening the voltage gated channels. Now we did cover this from chapter 9, so this should be a review. We're going to add millivolts, we're going to add voltages here, but we're really going to review exactly what we talked about already. So what do we need to know? Who are the key players, right? The voltage gated channels have two gates and alternate between the different states. Sodium going in one way and potassium coming the other way. So we have the sodium and the pink on the left, right? Closed at resting, open during depolarization, and inactive, right? Almost as soon as they open. Then we have the voltage gated potassium channels, right? They're going to be one gate, two states. So we're going to closed when they're resting and opened by depolarization after a delay. And this will become a little clearer as we look at the picture. All right, so here we are. Here it goes, the whole thing together. If we start on the top, right, you'll notice that there's sodium on the top. There's the membrane and the two proteins, potassium on the other side. This is the resting state. All the gated channels are closed. Now, there's a stimulus, number 2. So here we are on the right-hand side. The sodium channels open. Oh, remember that at resting state, we're at minus 70 millivolts. So at depolarization, there's a stimulus. The sodium channels open. Sodium rushes in. Sodium is positive. Remember, the inside of the cell is negative. If we start flooding all of those positive ions in, it goes from minus 70, minus 60, minus 50. When we get to what's called the threshold stimulus, minus 55-ish, then all of the sodium channels open and the action potential spikes way up. And you'll look at the little teeny tiny blue square. You'll see how it has that tall spike. It went from minus 70, and then we're throwing all that positive potassium in there, so it goes way up to a positive, sometimes all the way up to like positive 30. Once we get to the top, right, we're at equilibrium. Remember what this is, right? We have ions on two sides of the membrane. We're trying to equilibrate those, right? There were a lot of them out here and a few in here. Well, now it's the same. So that is equilibrium, the top of that little spike. So at that point, we trigger the potassium channels to open. It's fascinating. So when the sodium gets up here, that means the potassium levels are off. That voltage change, right, opens the potassium channels. That's the bottom. So you'll notice now the green potassiums start shooting out of the cell. So now we have a lot of positive in here. We're now putting positive potassium ions out here. We're trying to re-equilibrate. We're trying to establish that negative on the inside, positive on the outside. You'll notice at the same time, the myogram or the action potential, right, starts to go down. That spike starts to go down because now the negativity is returning. In some cases, number 4, we get to what's called a hyperpolarization event, and they actually, too many potassiums go out, and it gets a dip down. So the overall, we're at resting membrane potential minus 70. Sodium channels open, sodium floods into the cell. Positivity, depolarization. At equilibrium, potassium channels open, the potassium starts flowing out, it starts to return to being negative. And that's an action potential. Now, how do we recover from that, right? So we have resting, depolarization, repolarization, hyperpolarization, and then back to resting. We need the sodium-potassium pump to re-equilibrate the ionic conditions. Go watch this. AMP Flicks, Generation of an Action Potential. Go watch it. Important. So repolarizing resets the electrical conditions, not the ionic conditions. Right? When all the sodium went in and all the potassium went out, we now need that to go in the other direction. So now we have active transport of sodium and potassium across the membrane to reestablish those conditions. So we can go back again at that minus 70 and generate that loop. So not all depolarization events produce an action potential. So you can figure this out. If you take a piece of hair, let's see if we pick one out. I took two. So I'll take this one, this hair, and I run it across the back of my hand. All right, I can feel this. I feel it, which means that there was enough pressure, there was enough sensitivity, there was enough something to trigger an action potential. Because an action potential is basically saying something on your skin, pay attention to it, right? And so I'm doing this. I'm dragging this across the back of my hand, and I can feel it. So that depolarization event was enough to produce an action potential for me to know this. If you drag it across your palm, you will not feel that. Well, you might, but you shouldn't. Because remember, again, if we go back to our tissue, right, this is the stratum lucidum plus the stratum corneum. There is a thickness there. So this hair is not strong enough to produce a depolarization event. So for an axon to fire, for an axon to send a message, it must reach a threshold. And so this obviously reached the threshold for this tissue. This did not. All right, so usually that threshold is at like minus 55, right? And so this was enough because this is very thin skin. This wasn't enough to push down enough to feel that. All right, so we need, it's an all or nothing phenomenon. It's either going to go or it's not going to go. You're never going to get an action potential that goes up a little bit and down. It's always going to go choom, choom, choom. It's all or nothing. Now, it has to have the right number or the right amount of depolarization event, right, to trigger it. But it's an all or nothing. There's never a medium-sized action potential. It goes or it doesn't go. And propagation allows the action potential to be transmitted from the origin down the entire length of the axon because the voltage-gated channels are not just at the beginning. The channels are all the way down the membrane. So it changes here, and then it moves on and changes here as this part is repolarizing. Changes here, changes here. So this is depolarizing, this is repolarizing, this is hyperpolarizing, this is back. And it moves down the membrane. It's not happening along the length of the entire thing. It moves all the way down. So the depolarization here causes depolarization here, which causes it here, which causes it here. So it's like a domino effect once the threshold is achieved. Again, watch the propagation of an action potential, right? AMP Flicks. All right. So all action potentials are the same, but there are strong and weak stimuli. And how do we know, right? How do I know a light touch versus a heavy touch? It's the frequency and number of impulses received per second. So that even though the action potential itself is an all or nothing one-time deal, the number of them, when you get a number of them, right, the stimulus intensity will give the strong or weak message. So it's not about one being stronger or weaker, it's about how many. If I have 5, it's going to be this strong. If I have 105, it's going to be this strong. So here we go. So here we have the threshold. The sub-threshold stimulus does not generate an action potential, right? Couldn't feel it, right? I dragged the hair. So I dragged the hair, couldn't feel it. I dragged the pen, I can feel it, right? So maybe that's giving me that middle, that sort of 4 action potentials, just a little bit. I took something super heavy and went across my hand, right? The stronger the stimulus, the more frequently the action potentials are generated. So that one on the far right is a heavier, stronger stimulus, which causes more action potentials per second. So it's all about the number of them, the frequency, to determine how strong one of the stimuli is. One of the things we have to make sure is that we remember that this is an all or nothing thing. And so as the action potential is traveling down the neuron, if we are here with the depolarization, we're repolarizing, we're hyperpolarizing, right? This area right here is not really ready to do or trigger another action potential. So this is what we call a refractory period. A refractory period is going to be that period of time that the neuron needs to recover so that it can respond again. So there are absolute refractory periods that sort of is an all or nothing thing. Time interval in which the neuron cannot respond no matter how strong it is. We also have what's a relative refractory period. This is when a neuron can respond to an action potential, but it has to be much stronger. All right, so an exceptionally strong stimulus can do it. Because what you're saying is you want to catch it here, you want to catch it here and let it respond. Remember how we saw those muscle responses where we could reach tetany because it didn't fully relax? So if we're talking about that's a relative refractory period, if we're talking about that on a neuron. So we can get it to come up and it has to be really strong to go up again. Most of them are going to go up and down, up and down. So think of a disobedient dog. If he's absolutely refractory, he will never come when called. If he's relatively refractory, he may come, but only if you call him loud enough and you're angry, right? So that's what you can kind of use that as a little example. So we have these action potentials. They convey information. They convey information on stimulus strength by increasing in frequency, and they're all or nothing, and they need a little bit of a rest. They need a refractory period to reestablish that ion concentration. All right, so here we are. So here we have the tracing shows you the minus 70, shows you the stimulus at time 0, depolarization with all the sodiums flooding in. We reach equilibrium at the top, and we start to trend down. Now notice about halfway down, the window turns from that light green band to blue again. A darker blue, because the darker blue is saying it really needs to be a strong stimulus to make that goes back up again. Absolute refractory period in the green, you cannot get that to depolarize again. Because what are we talking about? We're talking about opening up all the channels and letting the sodium in. Well, they're already open. We're in a depolarization event. If they're already open, we can't open them again or open them more. The relative refractory period means some of them on this end have already started to close, right? And they're closing. So we might be able to get this section to go back up again, but they have to start closing in order for them to open up again. So absolute refractory period won't happen. Relative refractory period, we could generate a new one, but it has to be really strong. All right, so action potentials travel from neuron to neuron, and the speed at which these travel varies pretty widely. Now, reflexes, really fast. Glands, right, glandular secretions can be kind of slow. And so how are we going to, or how do they move? How insulated they are and how large they are. The larger diameter fiber has less resistance and they'll go faster. Large insulated ones, really fast. So it's large and insulated, super fast, small, not so fast, and non-insulated, they actually go quite slow when they're moving around. All right. So this is a picture of a non-myelinated axon. You'll see the stimulus is there, and notice how the voltage gets really small by the time it gets to the end of that dendrite. But here, notice how this one is myelinated. Interesting. Oh no, this is a voltage-gated ion channel. Sorry. This is voltage-gated channels regenerate the action potential at each site. So this one has one, this is on a dendrite, and then this one is going to be on an axon. And the axons, you'll notice, have a lot more voltage-gated channels going out so they can continue. I apologize, I wasn't reading it correctly. So that it can go down the axon. And this only gets more pronounced when you put some myelin around it. All right, so now we're at the end of the axon. We're at the axon terminal. We're at the synapse, right? We've been the synapse before when the axon rested on the membrane of the muscle cell. We can also have axons resting on the dendrites of another neuron. So we have a presynaptic neuron and a postsynaptic neuron. And neurons are going to talk to each other, right, by using, see, there's a little axon touching the cell body. We can have axons touching the dendrite, and we can have axons touching the axon. Axosomatic, axodendritic, and axoaxonal synapses. So they're just conveying information to the next neuron in the chain. And most of the synapses are going to be chemical, and we're going to secrete neurotransmitters, those different types of chemicals that transmit messages across the synapse. Because even though this axon terminal looks like it's touching, right, it's not conveying the electricity from one to the other. We have to have the axon terminal and then the next cell, whether that be a neuron or a muscle cell, chemical has to span that space. Just the way we saw acetylcholine go from the axon terminal to the muscle cell, there's just 50 or plus or minus neurotransmitters for each different type of neuron. Same thing though, axon, we need a neurotransmitter to go to the next cell. All right, so neurotransmitters, there are 50 plus or minus. They can exert several influences, right? So we don't know, they can be in one situation, we'll see this in the autonomic nervous system. In one situation, acetylcholine is going to cause sympathetic responses. In other instances, it could cause parasympathetic responses. So this video, again, an animation, would be great for you to go and watch on neurotransmitters. Different types of neurotransmitters are going to be acetylcholine, we have catecholamines, amino acids, peptides, purines, dissolved gases, all different types of things can be neurotransmitters. We're not going to spend a lot of time on them, but we will pick up on specific ones when we get to the peripheral nervous system. So less common, we have electrical synapses, all right? And these are joined by gap junctions. And remember way back in bio, gap junctions connect cytoplasm together, and you can have a rapid uni or bidirectional communication between the two neurons. So most abundant in embryonic nervous tissue, we sort of grow out of that as we grow and differentiate. But we can find some examples still in our eye movements and then in an area called the hippocampus where we have emotions and memory. But for the most part, we're back to neurotransmitters and chemical synapses. All right, so this is the end of chapter 11. I know it's a lot. I know I talk fast. I fully recommend you going and looking at all of the videos you can see for this information. Again, it is a lot, but I think you have enough resources out there to really get a handle on this information. Please bring any questions to class next week, right? And I will see you then.